Islamic mathematics. The Islamic Empire established across Persia, the Middle East, Central Asia, North Africa, Iberia, and parts of India from the 8th century onwards made significant contributions towards mathematics. Greece and India. They were able to draw on the fuse together the mathematical developments. Islamic prohibition on depicting the human form was the extensive use of complex geometric patterns to decorate their buildings, raising mathematics to the form of art. In fact, over time, Muslim artists discovered all the different forms of symmetry that can be depicted on a two-dimensional surface. The Quran itself encouraged the accumulation of knowledge. Golden age of Islamic science and mathematics flourished throughout the medieval period from 9th to 15th centuries. The House of Wisdom was set up in Baghdad around 810 and work started almost immediately on translating the major Greek and Indian mathematical and astronomy works into Arabic. Muhammad al-Khwarizmi, the outstanding Persian mathematician and an early director of the House of Wisdom in the 9th century, and one of the greatest of Muslim mathematicians. Most important contribution to mathematics was his strong advocacy of the Hindu numerical system, which is 1 to 9 and 0, which was soon adopted by entire Islamic world and later by Europe as well. Other important contribution of Al-Khwarizmi is algebra. Fundamental algebraic methods of reduction and balancing and provide an exhaustive account of solving polynomial equations up to the second degree. The 10th century Persian mathematician Muhammad al-Karaji worked to extend algebra still further.
Algebraic calculus. Al-Khwarizmi was the first to use the method of proof by mathematical induction to prove his result by proving the first statement in an infinite sequence of statements is true and then proving that then so is the next one. Al-Khwarizmi used mathematical induction to prove the binomial theorem. Binomial, a simple type of algebraic expression which has just two terms which are operated on only by addition, subtraction, multiplication, and positive whole number exponent such as x plus y squared. In 17th century, French mathematician Blaise Pascal, although many other mathematicians had studied in centuries before him in India, Persia, China, and Italy including Al-Khwarizmi. The coefficient needed when a binomial is expanded from a symmetrical triangle are usually referred to as a Pascal triangle. So, how to expand a Pascal triangle? So karon ipakita nako kung unsaon pag-expand ang binomial using Pascal triangle. So before na tan-awon sa nato og asa nagikan ang Pascal triangle. So consider the power of a plus b, so mao na atong binomial where a is atong first term ug b is atong last term. So ab raised to 1, so that is equivalent to AB. Then, if we get the square sa atong binomial na A plus B, so that is the square of binomial which is equal to A squared plus 2AB plus B squared. Tas, diri pud sa B cube, pud nato is equal to A cube plus 3A squared B plus 3AB squared plus B cubed. So, kung mapansin ninyo guys, ang atong polynomial kay naay gina-follow nga pattern. So, itry nato i-list down ang tanan nga coefficient sa atong polynomial. So, example diri sa atong n is equal to 1. By the way, ang n nato is mao na ang coefficient sa atong binomial. So, if n is equal to 1, unsa ang coefficient sa atong polynomial? So, ang coefficient sa A diri is 1 ug sa B pod kay 1. Then next, if n is equal to 2, ang coefficient po nato is natay 1 followed by 2 ug last term na coefficient na 1. So a squared plus 2ab plus b squared. So mauna siya ang coefficient sa n is equal to 2. Then ang next nato is n is equal to 3. So ang coefficient sa a plus b cube is 1, 3, tas 3 og 1. So mao na siya ang a cube plus 3a squared b plus 3ab squared plus b cube. So as you can see guys, kung magpadayon ng atong pag-expand sa binomial gamit ang exponent nga 1, 2, 3 up to 8, makahimo ta og triangle. So unsa ang pattern nga makita nato? So kung mapansin ninyo, ang first number nato which is kani ug ang last number sa kada na row is equal to positive 1. Tas ang naa sa tunga nga value is naapoy pattern. So pagkita nako sa inyo og giunsa nato pagkuha si 2 diri sa atong triangle. So kung mapansin ninyo, ang 2 diri mauna ang sum sa duha ka number sa taas which is 1 ug 1. So if we have 1 plus 1 equals to 2. So try nato sa uban sa row 3. Ang 3 dira is mauna ang sum sa 1 plus 2 nga naa sa second row. So 1 plus 2 that is equal to 3, tas 2 plus 1 equals to 3, then another sa row 4 na punta. So ang 4 pud nato diri mauna ang sum sa 1 plus 3, so mao na equals to 4, tas 3 plus 3 is equal to 6, tas 3 plus 1 is equal to 4. So makahimo ta og Pascal triangle gamit ang mga sum sa kana na number. Og mauna siya ang ginatawag nga Pascal triangle. So karon, ginaunsa ba paggamit si Pascal triangle in expanding a binomial? So let's have a example. So natay example. So use Pascal triangle to expand a plus b raised to 8. So diri, since ang n nato is equals to 8, gamiton nato ang 8 row nato dito sa atong Pascal triangle. So ang 8 row sa atong Pascal triangle is ang kani 1, 8, 28, 56, 70, 56, 28, 8 ug 1. So, mao na siya ang coefficient or n nato nga gamiton nato kay a plus b raised to 8 man. So diri guys, gamit ang mga number na nakuha nato sa mas madali ang atong polynomial. So, una is para makuha ang first term sa atong polynomial, first kopyahon nato ang 1 muna siya ang atong first term, ay first coefficient, then multiply to a or ato ang first term, then b is ato ang second term. So karon napud tay pattern pag adto nato sa exponent sa atong mga variables. So diri ang n nato is equal to 8. Ang a nato guys is mag-start kay 8 and starting exponent pod ni b is 0. Tas next term na pod ta. So plus next term we have 8. So 8a times b, tas ang exponent pod ni 8 is, sa A is mag minus 1 lang ta. So, sa una, di ba, katong kuan kay 8 man tong exponent dito. So, minus 1 lang ta. So, since 8 ang exponent dito, 8 minus 1, so equals to 7. Then, second term nga coefficient sa B is mag plus 1 lang pud ta, which is 0 plus 1. So, B is raised to 1. So, proceed ta sa next, which is plus 28. So, applying lang yapon ta same procedure. We have 28, A, minus lang yapon ta. So, A raised to 6. Then, B is mag-add lang yapon ta. So, B is equal to, I raised to 2. Kay 1 plus 2 man. So, sa exponent sa first term, minus lang ta. Ta sa second term pod, add lang yapon ta. So, proceed na pod ta, padayon lang ta padul sa sa next, which is ang 56. So, A is raised to 5, then B is raised to 3. Then next is 70. So, 70 times A raised to 4, then B raised to 4. Tas, followed by 56 times A raised to 3 times B raised to 5. Followed by 28, A raised to 2, then B raised to 6. Then, followed by 8, A is raised to 1, then B is raised to 7. Then last is 1, so 1 A raised to, kay 1 man ang una, so minus ta, so 0. A raised to 0. Then B, since ang gisundan niya is 7, so add ta, so B is raised to 8. So if mahumanan nato, then ato ara dayon nang i-simplify. So 1 times A raised to 8 is equal to A, then 1 times B raised to 0. By the way, numbers that raised to 0 is equal to 1. So, pwede ra na wala. So, next is 8 times A to the power of 7. So, 8 A 7, then B, kay 1 man. So, plus 28 times A, so 28A 6, B squared plus 56 A to the power of 5, then B to the power of 3, then plus 70 times A to the power of 4, then 70 A to the power of 4, then B 4, plus 56 A cubed plus B 5, plus 28 A squared plus B 6, plus 8 A plus B to the power of 7, and plus, so 1 times A to the power of 0, so equals to 0, or 1. So dili na nato ibutang. Then ang ibutang na lang is B to the power of 8. So therefore, ang expanded form sa atong A plus B raised to 8 is equal to this polynomial. So, gets?
Omar Khayyam, perhaps better known as a poet and writer of the Rubaiyat, but an important mathematician and astronomer in his own right. He carried out systematic analysis of cubic problems, revealing there were actually several different sorts of cubic equations. He also identifying the foundations of algebraic geometry. He was held the advantage of inability to separate the algebraic from the geometry method for the solution equation had to wait 500 years in the Italian mathematicians Del Ferro and Tartaglia. Nasr al-Din al-Tusi, in the 13th century Persian astronomer, scientist, and mathematician, and the first trigonometry as a separate mathematician discipline distinct from astronomy. Abul Wafa Buzdani and Abu Nasr Mansur was discovered the spherical triangles, and Arab Tabit ibn Qara, who developed a general formula by which amicable numbers could derive, rediscovered and later by both Fermat and Descartes in 9th century. Muhammad al-Kharizmi, one of the first directors of the House of Wisdom in Baghdad in early 9th century, was astounding Persian mathematician. Algorithm is derived from the Latinization of his name, and the word algebra is derived from the Latinization of algebra. Al-Kitab al-Mukabasar fi Hisab al-Jabar wal-Mukabala means the comprehension book on calculation by completion and balancing. In particular, Al-Khwarizmi developed a formula for systematically solving quadratic equation by using the methods of completion and balancing to reduce any equation to one-sixth standard forms, which were then solvable. Geometric proof by completing the square follows. Al-Khwarizmi starts with a square of side x, which therefore represent x squared. On figure 2, to the square we must add 10x, and this done by adding 4 rectangles each of breadth 10, 4, and length x to the square. And for the figure 2 has area x squared plus 10x, which equal to 39. We now complete the square by adding the 4 little squares each area. 5, 2 times 5, 2 is equals to 25, 4. Hence, the outside square in figure 3 has area 4 times 25 over 4 plus 39 is equals to 25 plus 39 is equals to 64. The side is of length 5, 2 plus x plus 5, 2, so x plus 5 is equals to 8, given x is equals to 3.